Hello everyone, welcome back to lesson number 20 for Calculus BC. We're talking about Extrema, and I told you guys in video 3 I would do a review of all of them, but I thought, well, let's go ahead and learn how to do the absolute max and min, and then in the fourth video we can summarize it by doing every single thing and show you guys how easy that really is. So let's now talk about the absolute max and min. And I just want to say very quickly before we do that, and I'm going to draw a little picture right here. So the difference between relative max and min and absolute max and min is kind of pretty counterintuitive, I think, here for you. So if I give you something like this graph right here, then you guys can see that there is a relative minimum here, and then there's a relative minimum here that ends up on this interval. If I'm just looking at just this interval right here, this is also the absolute min. Right? This is the absolute furthest down that we have fallen. And then if we look at our absolute maximum, there's a maximum here. This is a relative maximum. There's a relative maximum here. And then there's also a relative maximum here, which ends up being the absolute maximum. And the reason I drew this picture this way is because our absolute can not only be where our derivative is equal to 0 or undefined, it's actually also, we have to look at our endpoints. We actually have to look at our endpoints. So that's the difference between the two, and so let's do some examples of it. Before I do that though, I want to just show you guys or talk to you about this theorem. So the extreme value theorem is pretty straightforward. It says if you have a continuous function and it's got to be on a closed interval. So if you have a point A and B and you have 2 points somewhere here, if you have a continuous function, no matter what you do, so if I draw a straight line through it, I will have guaranteed an absolute max and min on the interval. Well, if I draw a straight line, then my absolute max is at f equals a, and my absolute min is at f equals b. Well, let's say I didn't draw a straight line and I did something more like this. Then obviously my absolute max would be here, my absolute min would be there. So no matter how you start drawing this, no matter what you do, again, it's got to be a continuous function. And it's also got to be a function, so you can't do something like that, right? You can't do something like that. It's got to be a function. So that's why it's really important to do that. So if you have this, you can do something like that. Well, here's your absolute max, and then your min is also here at B. So no matter what you draw, hopefully you guys are getting the point, you're going to have an absolute max or min. So this is, we have an IVT, now we have an EVT. So extreme value theorem says exactly that you're going to have an absolute max and min. So let's actually show you an example of how to find the absolute extrema for the problem. Notice the word says absolute. All right, so we're not looking for just relative extrema, we're looking for absolute extrema here. So the first thing we're going to do is, and this is also a first derivative test, but kind of sort of not really. What I mean by that, because I was like, that was very vague. What I mean by that is you do have to first of all find the first derivative. You still got to find the first derivative. So it's not really a first derivative test because we're not going to plug it back into the first derivative. So I apologize for that. So we find the first derivative, and we're going to still set that equal to 0. And we're going to go ahead and figure out what value of x makes our first derivative 0. In this case right here, x is going to be equal to 3 over 2. So 3 over 2. So what we're going to do now is we know there's at least a relative min or maximum here. But what we got to do now is we want to do a table, and we're going to put x here, and we're going to put f of x here. For absolute, we want to know, looking at the overall graph, right, what value of y is going to be the biggest and the smallest. So we don't want to plug back into the derivative. We don't want to know what the behavior of the derivative is. We want to know what the values of the actual function is. You still have to also include your endpoints. Now, for absolute endpoints, you have to include the endpoints for absolute. For relative, never, ever, ever. You also want to make sure that this number is in between this interval. If it's not, then it doesn't matter because we only care about what's going on between 1 and 3. So I go ahead and put 3 halves here just because it is in that interval. All right. If it's not, we don't count it. And then all you do is you plug in your values for 1. So I plug in 4 times 1 minus 12 times 1 plus 10. And with the beautifulness of my paper here, I know the answer is just going to be 2 to save us some time. If I plug in 3 halves here, and you can use a calculator for this particular thing, you're going to get 1. And you plug 3 into this, you're going to get 10. So these y values are going to help you determine whether there's an absolute max and there's an absolute min on this interval from 1 to 3. All right. So we look and see what's the highest y value and the lowest y value. So the highest y value is actually at 10. So we have a absolute maximum here, and you would say that it's at x equals 3, and the actual value is actually equal to 10. All right, and sometimes usually this is a legit answer for you on the exam. An absolute max at x equals 3, y equals 10. And then our absolute minimum, and I like this example because it's not the smallest one, it's actually right here, right? This is going to be smaller. So this is where we're going to have an absolute minimum. And this is going to be at x is equal to x equals 3 halves, and then y is equal to 1. Okay? So that's what you do for the particular point. Now, usually for absolute, we're going to give you guys endpoints. We're going to give you endpoints. However, there are going to be times where you're not given endpoints. All right, and this is more so BC than AB. So if you're an AB student and you listen to this, you probably don't have to listen to this example. But for example 14, what if we don't give you endpoints? You know, and that's pretty okay. You just want to, first of all, when you're looking at these questions about the endpoints, figure out what the behavior of the graph is. So I know, based on my knowledge of polynomials, that this is an even function. So I know it's an even function because there is the highest degree is an even number, and then the leading coefficient here is positive. So this is an even number, and it's positive. So since I know it's even and positive, I know the behavior of my graph is going to look something like this. Something like this, right? So no matter what this power is, you can plug something in your calculator, have fun with it. It's always going to go up and up. Now, if this has been negative, I would go down with it. So what this is telling me is that I know right off the bat that there's going to be no absolute maximums, right? I know there's no absolute maximums because we can go on for infinity, 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 infinity. But I know that there's got to be at least a couple, if not some, maximums. I mean, this graph could, come down like this and do like this too. So, we could have relative max and mins for sure, but we know there's no absolute max here, right? So I could have a relative min here, a relative max here, and a relative min here. So this is just guaranteeing that I know I don't have an absolute max. And so how do we, continue the problem? Where we're going to go ahead and find our derivative, which we're going to get 4x cubed plus 4. We're going to, if we want to factor out the 4, which we can, we're going to set this thing equal to 0. And we're going to x is equal to -1. Now, if we had multiple things here, multiple critical values, then you would actually, plug them all in. The difference between a relative max and min here is we're just, and there's only one of them. So, I mean, you guys can kind of see what we're going to do with this. But so if we plug in -1 to our function, we're going to get that this value is going to be -3. And so we know that there's going to be an absolute minimum at x equals -1, y equals -3. And, we could essentially, if we wanted to, do our null number line, and look at our first derivative just to see the behavior of the function. And if I plug in something like 0, I'm going to get plus. If I plug in something like a negative or 2, I'm going to get a negative value. And so as we're going down, and then going back up, we can see we also have a relative minimum here. So, I mean, it's just kind of the icing on the cake to actually do stuff like that. So that's the idea that we're going to have for that particular problem. Over here for question number 15, I know some people maybe were looking at that problem. Again, this is more so for my BC students. If we were to find this derivative, which, I would highly encourage you guys to rewrite this problem, since it, there's a constant in the front. On the top. So go ahead and write it like this. Let's find this derivative for a second. Because let's say we don't know what this graph looks like. And quite honestly, you may not know what the graph looks like, but you don't need to know that for this particular problem. So to the 1 less power times 2x. All right, so here's our first derivative, right? And so let's go ahead and simplify this just a little bit nicer for us. So it's going to be -2x on the top, and it's going to be 1 plus x squared over 2 on the bottom. Now, if I ask you guys to find critical values, the critical values for this. Well, the first thing that you would do here is you would actually set your numerator equal to 0, and you're going to get x equals 0, and you would also set your denominator equals 0. All right? Because again, critical values are where your numerator, your derivative is equal to 0, and where it's also undefined. Well, this is never going to be 0. It's never going to even be negative. It's always going to be positive. So this one just doesn't really matter. So we don't care about that. So all I care about right now is x equals 0. Right? So I just care about x equals 0. So if I go ahead and plug x equals 0 in here, I'm going to get the value of 1. So I know this is a relative something, right? I don't know if it's a relative max or min yet, but I do actually know if it's a relative max or min. And then we're going to talk about that in a second. But I know this is this is an absolute something. It's either absolute max or min. Well, how do I know this? What do I know from previous lessons that can help us out with this? So guys, remember, we don't have any endpoints here. So then we can take the limit as x approaches both positive and negative infinity of 1 over 1 plus x squared. What is the behavior of this graph as it approaches positive and negative infinity? Well, you guys realize that this function is, you guessed it, bottom heavy, so I know that it's approaching 0. It's approaching 0. So as my graph is going towards positive and negative infinity, it's actually going toward, and remember, wait, there's a point 0, 1 here, right? 0, 1 is this. And so it's approaching 0 here, approaching 0 here. So you guys realize that this has to be our absolute maximum. It has to be our absolute maximum. Okay? So looking at the behavior of the graph is really helpful for this if you don't have any endpoints. And like I said, most times you're going to have endpoints. But I'm just showing you guys 2 strategies if you don't have them. And then over here, think about, oh, maybe the limit. What happens if the limit goes to positive negative infinity? If it's bottom heavy, well, there you go. Your answer is 0 for this. And if the point had been 0, negative 1, then this would have been an absolute max, or minimum, absolute minimum. All right, so next video, we're going to put it all together. And so I'll see you guys then.